Navier Stokes equation. Equations. Components. Component forms. Navier Stokes equation, components form. So, and let us go back to our momentum equation, Navier Stokes equation, for an incompressible fluid, which is said is what? That is dq dt is equal to minus 1 over rho grad p plus mu del square q plus, oh, let me write this one as nu, because that is kinematic viscosity plus 1/3 nu kinematic viscosity of grad dq. So we know all this. But in the case when it is incompressible, of course this one will go. So let's treat this generally. So it is quite possible that we wish to expand this in the component form, like this is the vector form of it. So if you want to write, this is vector form. Vector form, and of course we can actually put it in tensor form. That is not strange to us. In tensor form, Q is what? In tensor form, we may say that the velocity of the fluid Q is equal to what? Ui. Velocity of the fluid Q is equal to Ui, where I is what? I stands for 1, 2, 3. So where I is what? And 1, 2, 3. That is to say, that means it's the same thing as say that Q is equal to U1, U2, U3, of course, which corresponds to, in our translation, that means this is going to be what? That is U along X, if it is rectangular, B, that is in rectangular coordinates. In rectangular Cartesian. Coordinates. Now, the tensor form now will be what? So, this now corresponds to the Ui, since this is the vector form of it. The t is equal to minus 1 over rho. Grad now is what? Grad, that means we are differentiating respect to xi, say, of what? Of p. Of course, this is so. If you remember that grad, this is grad, you know? Grad p is what? Is di x, say, of p, di y of p, di z of p. Of course, if in Cartesian form, you may say that your x as a vector can be written as x1, x2, x3. Because if you like, this is the same thing as what? xi or xj. You can use xi, you can use xj, because indices are dummy. So where I is what? I is 1, 2, 3. Of course, if you want to use the rectangular coordinate system, this would have been x, y, and z. Because that is not strange to us. So in that wise, that means we are very completely sure that grad p is simply what? Our graph P is simply in tensor form, that is di P di xi. Of course, by the time you say that your xi, by the time you say that xi is 1, 2, 3, of course, you have fulfilled this condition. Which, of course, if you like, you can still say that this is di P di x1 di P di x2 di P di x3. So vector form. So this corresponds to this. So by writing this like this, it is really justified. Di P di xi. So let us now come here. The plus mu. Of course, this also goes the same way. This can actually be written as okay, di x j squared of what? Of q. You can actually write it, you can actually say di xi squared. It's still the same, because in tensor analysis, you know that the index, the subscript index, is always dummy. If I like, I can change this to j, I can put it as k. What is important is that the variables j, variable j stands for what? Stands for, variable j stands for 1, 2, 3. So in tensor, you are free to use any initial notation, but you will see the advantage of not using I here, why I decided to use j, because q is a vector. Q is a vector, and then q has components what? 1, 2, 3. And if you like, you want to put it in this form, if you want to write it in the tensor form, of course, I can just say this is q what? Q substitute what? Substitute I. That means, or if I like, I can say it is u substitute what? Substitute I. And that takes care of this form. That takes care of our u1, u2, and u3. So this one is in vector form because q has to be written in tensor form. So that means this q, if I like, I can use qi. So, and I don't want I to be repeated here. That's why I did not put j. That's why I now change it to j. Because if I put qi here, and if it is repeated, of course, that means it is divergence. And I don't want to use that. It will cause confusion. In as much as we know what we are treating in tensor analysis. So that is the reason why I'm not using I here. I've told you the reason here. Now, I want to write this. This again is nu over 3. Then grad. Grad is half. You know that grad has one component. It has, if this is grad can be written as di x, di y, and di z. And if I want to use indicial notation, I can actually write this as di x1, di x2, di x3. Of course, in a tensor form, therefore, this can just be written as di xi or di xj. Depends on what you intend to. So if I put j, for example, I put it as di xj. So without loss of generality, I can say this is di xj. If we lose di xi, it is equally correct. It is equally correct because letters are dummy. Even if I like, I can say it's di xa. In as much as k, take the value of 1, 2, 3. So therefore, this one I can write it as di xj. Of course, divergence is not strange to us again. What is divergence? Div q. Div q is what? It's not a strange thing. So here, Your div q is what? Div q, of course, is going to be, remember, if you write q with tensor form, that is going to be what? That is going to be di what? Di ui di x I. Di ui di x I. Because this is repeated. So that means this is just like the u1 when indices are repeated. So that is summation in tensor analysis. So that means this is just simply what? The u1 plus, so the u1 the x1 plus the u2 the x2, because the index here must agree. Then finally the u3 the x3. So that is initial form of that. Or of course you have done this. This is simply what? That is just going to be di u di x plus what? Di v di y plus what? Di w di z. In which case this is what? u2 and this is what? u3. Of course this is x1, this is x2 and this is x3. So we are justified to put the tensor form like this. Or else, and as I write it like that, and I'll put this as your div q, if you like. This tensorial form. But because of space, that's why I just left it like this. Because of this. Because you know, this in tensor form is simply what? This is simply going to be the u1, that is the ui the xi. What is important is I can put k here, the uk, the sk. What is important is that it is repeated, and when it is repeated, it is addition. So I hope you are following the class. Now, situation if it for incompressible fluid, of course, if it is incompressible, this one will go, you know, and this one will go, so that you are not left with this and what? And this part for incompressible fluid. Okay, I think we have explained that aspect, so we can now proceed. Now, the component form now. In component form, my intention now is to write the expression for Navier-Stokes equations. My intention is to write it in terms of rectangular Cartesian coordinate systems, that is x, y, z, and also I intend to write it in curvilinear coordinates, because most problems in life are not always in rectangular. So we write it in cylindrical coordinate form, also in spherical coordinate, because those are the common ones, and so on. So let's now proceed. And this is just for explanation. Now, let us now break them down now. So I want to write the component form of the vector form in components. Since Q, as I said, we know our Q, so Q is what? So it's a, don't forget Q has 3 components in rectangular coordinate system. That is the first one I want to treat. So rectangular Cartesian. Rectangular Cartesian coordinates. In rectangular coordinates, how do we write the components of coordinates form? So that is, how do we write this? Of course, because we know that Q has 3 components. Let's still conform with our U, V, W in rectangular coordinate system, where U is the components along x-axis, V is components along y-axis, and W is the component along Z. Of course, you can break this down. And in rectangular coordinate system, position vector x, a position vector, some people use this as position vector. You pick any point in space, that point depends on what? X, Y, and Z. That's position vector. That is, of course, this is an advanced class. Position vector is just the vector of a point related to the origin. So if it is related to the origin, the component x, y, z, like you can as well put it in a tensor form. Now, what else do we need here? We need also del square. We have not treated del square. Del square in component form. This is just going to be what? This is di x, di y, di z. Of course, because del square is the dot product of del and del. So this, of course, you know, this is del operator, which is a vector. It depends. Vector is gradient, and the donor operator. Then you dot it with itself. If you dot it with itself, you take the dot product with itself. Of course, correspondingly, the answer is going to be what? Is additive. Additive of all so here. So this is simply what? So this will have given us what? This will have given us di2 di x squared as an operator plus what? This and this, di2 di y squared, and finally di2 di z squared. So that is that. That's the meaning of that in a rectangular coordinate system. So you can see clearly we have done almost everything. That means what is left is just to put q there. Because this is a vector equation, everything here must be vector. It must be vector. If it's not vector, that means you are writing rubbish. Now, the next now is we know this. We've already treated this. So without loss of generality, I cannot put what? Without loss of generality, I can write the tensor form of this as what? The tensor form of this, that means I have di what? I have di q. Instead of q now, di t, dt is total. dq, dt. My q is what? Is what? U what? U along s, b along y, and w along z is equal to, I have this, that is minus 1 over rho grad p. My grad p is simply what? Is, you can see, just put p here, So that means I will have di p, di x, di p, di y, finally di p, di z. That is this part, because grad is already this one. This is del operator. But when you put p here, don't put p here. That is grad of p. So the component, so you can see I've written that. Then I'm now left with what? With this one now. Del squared, of course, is already, it has been established earlier. Okay, this is del squared. This is del squared. So just put it here. That is di2 di x squared plus di2 di y squared plus di2 di z squared. Okay? Of what? Of q. But what is q? This is q. Q has how many components? It has component what? It has component u, v, w, u, v, w. This is q, because our q is what? Because our q is u, v, w. So I put it there. So that means I can list this thing out in component form. We can list this thing out in component form. So let's start with components along x-axis. Along x-axis, what are the components? That is along x-axis, what are the components of this? So along x-axis, therefore, along x-axis, the velocity component along x-axis is u. So I will pick this. So along x-axis, therefore, the component form of Navier's equations. Along this, that is what I want. That means I will have du dt is equal to, I will pick the component along x-axis there as well. since I'm writing in terms of component, that is minus 1 over rho di b di x. That, so I'm taking this. When I get to this stage, I forgot to write this. I stop here. How about this? I forgot to put this. So I have to add it to this expression. That is plus what? I'm still here. Plus 1/3 mu. Of course, we already know this. We have already done this before. Grad is what? Grad has, I've cleaned it. Okay, grad is just like this. Just di x, di y, di z. So grad is di y, di z. So I have di x, di y, di z. This stands for this. That is del operator. Hamiltonian operator. Then this, of course, div q. We already know it. Div q is what? Div q, if you like, you can put div q there. Or if you like, you can put this expression for div. Div is what? Div is just, after the under continuity equation, you used to come across it very often. So this expression is very easy. You can call this expression is what? Is div q. In this case, that is going to be what? Di u, di x, plus di b, di y, plus di w, di z. So this is the expression for what? This is the expression for this. Di z is standing for div q. This is div q. This is div q. Of course. So that means I'll put that there. Or sometimes if it is too long, and this is very, you can still even write it as div q, since we know the meaning. So this is going to be, so div q is what? That is going to be di u, di x, plus di b, di y, plus di w, di z. So it is complete now. So you see, I've almost forgotten, but realizing that we are writing component form, I pick this, then I know something else will be picked. So after picking this, I need to pick the components. This is the component because this one is just a scalar operator. So it is this that I will apply on the whole of it. So next, I've written this, I want to write this. So that is plus new. Don't be tempted to write only this. It is the whole, because it's not a vector, it's just a scalar operator, which is del squared. So this is going to be automatically called a Laplace operator. So that is going to be what? That is di 2 di x squared. You know, it is this one I'm using. That is of u plus di 2 di y squared of u plus di 2 di z squared of what? Of u. Everything is in terms of u, because here I'm writing the components of x. So this is along x. Then finally, this last one, due to compressibility influence. So that means plus 1/3 mu. I want you to look at this very well. 1/3 mu of what? You see, this one is a known value, it's a scalar. So the component I'm taking is this. When I take this component, it will operate on this only. I've not yet taken the component of this side, but this one is what this one acts upon. So that means I have di what? That is di x of what? Of di x of what? Of what is here? Which is di u di x plus di b di y plus di w di z. Successfully, we have written in component form the S part of the equation of motion, that is Navier's equation. So the Navier is a very, you can see the equation is a big one, but in the absence of body force, if there is body force, there is no problem. Just put force acting along x-axis. So if I want to put body force, if I included body force, that means if I want to put body force, look at this relation again. That means I would have put body force per unit mass in that. So if I want to add body force, to this, because a force, generally a force, if this is a vector force per unit mass, it will have three components. One along x, let me represent that, along y, along z. But if you don't want to generalize this, if you want to generalize it in tensor form, that means this is F1 along x, this is F2, this is F3. So I want to put this in tensor form, that is F subscript 1, subscript I or J, where I is 1, 2, 3. Okay? So if I want to add body force by unit mass, that means this is in tensor. So what I'm going to put here is what? F what? F I. This is not a vector, but it has three components. So that's added. So if I want to add the same to this, in a general case, that means I'll add what? The component along x is what? Fx. So that will be added. So that means the general form. Where F, don't forget, is body force per unit mass. F1. That is the body force acting along x-axis. Similarly, we follow the same trend. Similarly, along y-axis, I'll pick this. Along y-axis, I will pick this. It is B I'm going to pick. I will pick this one, V. Along y-axis, I will pick this. Then translate it into components form. So in that wise, we shall have so in consequence, along y-axis, similarly along y-axis we have what? Along y-axis. So the component will be what? The component will be, I will pick this. That's dB dt. dB dt is equal to minus 1 upon rho. Along y-axis, of course, this is what is along y-axis. So this is what I'm going to pick. Minus 1 over rho of what? Di p di y. Di p di y plus, we are now here. So that is, again, that is new. Of what? Of, I'm picking it along y-axis. You see, this one is a fixed scalar operator. So what I'm really picking is this V. So that means I have di2 di x squared. Let me write it the way we wrote the other one. You can see. This is just it. So we are just replacing 2 by what? By V plus di2 di y squared V plus di2 di z squared V. So that is what we have really done. So then, that is that. Since it is this one we pick, that operates on that. And then now, we are now picking this for the compressible part of it. That is plus 1/3 plus 1 over 3 nu. 1 over 3 nu of course, this time around, this is what we are picking. Where is it? Okay, where is it here? Okay, this is it. I'm picking this. This is 1/3 nu over 3. Are you with me? So it is this one that I will operate on this. Just as I pick this and operate on this. So I'm picking di y into that. So that is di y. Di y of exactly the same thing. So exactly the same thing. So except that instead of U, we now put what? Okay, exactly the same because it's divergence. So it involves di U, di X, plus di V, di Y, plus di W, di Z. So at this stage, we have completed it. And in fact, if you look at the first two equations above, if you look at this first one, look at it, you can see it's similar to this. But if we now remove U, what if it is along x-axis? It is x. If it's along y-axis, change it to y. Okay? Similarly, instead of U here, you can see that what we have here is V, which is the component of velocity along y-axis. And when you come here, just remove this U. You can see U here, U here, U here. Replace it with V. You get everything here back. Then plus, what really changes here is, you can see this is di X. But this time around, it is now di Y. You still put exactly the same thing. This is di Y of exactly the same thing. Then, in the case of body force, you can always do that. The components of body force along y-axis, we represented it by what? By F2. By F2. So, in the case of x-axis, it was F1. Then with this now, I think you can translate the last component along z-axis. So following the same way, you can see that along z-axis, without loss of generalization, you can say that it's going to be what? You can see there, this time around, the W, you have to pick all W component. That is the W, the T, the W, the T, the W, the T is equal to -1 over rho, di P, di what? Di P, di Z. Di P, di Z. You can see it clearly here. Di P, di Z. Then all of that follow the same trend. So, or clearly you can see this is this. The only thing is that this time around we remove W, we remove V and put W. So di 2W, di X squared, di 2W, di Y squared, plus di 2W, di Z squared. So that's it. Of course, it's obvious from here. And this one follows the same trend, 1 over 3 new. Instead of di Y, this time around, you know, it is this we are going to use on it. So that is di Z of, again, di X, di U, di X, plus di V, di Y, plus di W, di Z. Again, if you want to include the body force, the components of body force along z-axis is F3, as we said. So the three equations are the component form of Navier equation in Cartesian, in rectangular Cartesian coordinate system. You can see that this is the components of Navier equation along x-axis. This is the components of Navier equation along y-axis, and these are the components along z-axis. Of course, look at them; they are similar. Once you know one, you know the rest. By the time you know that of first the component along x-axis, you can see it is U. You see U, just put U there, and here, no, partial derivative in terms of x, because it's along x-axis, then plus the force along x-axis. You can see it's the same thing. So knowing one, you know all. So you don't need to start bothering yourself to be cramming, to be memorizing your unnecessary things. The same thing when you put V, that means remove U from that expression, put V. This is respect to Y, because this one is respect to X. So all of that I can see is the same thing, except that we have removed U there, then put V there. Then instead of di X, now it is di X, the same thing there, then F2. And of course, from this, the third one now follows. That instead of U again, just put W. Then, because along Z axis, that is differentiation return to Z axis. And of course, just W replace, and now put it. So it follows the same trend. So if you know one very well, others follow the same trend. If you know one very well, others follow the same trend. Now, I intend to write this also in next We have treated rectangular coordinate system. Now we want to teach a very common coordinate system, which is a cylindrical coordinate system. In cylindrical coordinate system, okay, let me still do this. So now that we want to write the components in cylindrical coordinate system. We want to write it in cylindrical coordinate system. In cylindrical coordinate system, again, in cylindrical coordinate system, we want to write Navier equation cylindrical. Coordinates form, and want to write coordinate form of Navier Stokes equation in cylindrical coordinates form. Of course, in cylindrical coordinates, remember that in cylindrical coordinate system, the system where you have this as a cylinder, this as a cylinder, this as a cylinder, and let's say that this is z-axis, this is z-axis, say this is x, y, and z axis. Say this is origin. So if you pick any point on the cylinder, suppose I pick a point on the cylinder, surface of the cylinder, then this distance, if you like, you can call it x, you can call it r, just as I mentioned earlier. You can call it x vector, you can call it r vector, if you like. But what is important is that if you trace this, here, if you project this down, well, you must have done that. So what I say is that this is x. If this is normal x, y, z, if it's a point, which is x, y, z, you can actually write it in terms of angular movement. That if you are tracing this down to this, and this angle, if this angle is theta, and this length is r, so in cylindrical coordinate system, if this is r, that's what I was just trying to put here. That is r, and this is theta, and of course along this, that is z. That is z. Then that is why you have this here. To get to this point, you move along x-axis, say a distance x. Then you move straight to cover a distance y. Then you climb up to cover a distance z. That's it. But in the same sense, you want to write this in the cylindrical coordinate system, you can see you don't need to move like that. It depends only on this distance r. The same on r, radial distance. Then it depends on this angle theta. Then you climb up. That climbing up is not changing. It is still z. So that is z. So this is what we are transforming into. So that means in cylindrical coordinate system, the position vector of any point relative to the origin, any point, if you like, some people use r, some people use x. So if we use r or x vector, it has three components: r, theta, and what? And z. Because we've done this earlier in our previous class before the short break. Now, then we can actually write this. We can transform, and the velocity in this case is what? Velocity of the fluid is still q, but we say that the component along r is qr. That is, qr is along arc of velocity, and along theta it is q what? Q theta along theta, and along z it is qz. Of course, in some textbooks, some people they will still say this is u r, u theta, uz. So don't be confused, it's still the same thing. Or some may even use this as VR, B theta, BZ. That reminds me, you see, in fluid, sometimes you can represent this by velocity Q's, or if you like, you can use this notation to represent velocity as well. So that is no problem. So now, our interest now is to transform. Our interest is now to write the equivalent in cylindrical coordinate system. To write the equivalent in cylindrical coordinate system. But well, this I don't want this to waste our time because we have treated this coordinate transformation under orthogonal transformation geometry. We've done it, and I even gave you some assignments there to do. That is, if you have done it at all. So there, we said that we talk about scalar factors. There are the scalar factors, h along r, which stands for your h1. H along r in cylindrical coordinate system is 1. h2, which is h along theta, is r. And h3, which is h z along z, is also 1. This we have done. Then, apart from that, we treated some transformation that del, if you want to write del operator generally in a curvilinear coordinate system is what? This is a revision of what we have done. This is 1 over h1 die u1, 1 over h2 die u2, 1 over h3 die u3. So that's that operator. And don't forget, in curvilinear coordinate system, instead of x, y, z, it's not rectangular because they are curvilinear die. Curvilinear, just in form of curve. That this, of course, I remember done it for you in the class. You can see. So if this is, this is not a straight line. If this one is, the coordinate is u1, and this one is coordinate what? This is coordinate u2, and this one is coordinate what? u3. So that's the type we are talking of. And the scalar factors are along this one, this is h1, along this is h2, along this is h3. Curvilinear. Any type of curvilinear coordinate system, by maybe there's cylindrical, spherical, and other shapes. Okay? Now, in that wise, you just need to substitute for your, but I'm not going to do this in detail because I will jump, otherwise I'm spoiling you. So, that means in cylindrical coordinate system, then it will simply what? This is 1. So that is, and our u1, in cylindrical coordinate system, our u1 corresponds to what? u1, see, in cylindrical coordinate system, see, this one corresponds to u1, this one corresponds to u2, this one corresponds to u3. So therefore, that means this is 1, die what? Die r. This is r, die theta, because theta corresponds to u2. And finally, because this also is 1, so that is die z. So that is it in a cylindrical coordinate system. And you can always find the rest. Like, it is not difficult to find deep Q. It's not difficult to find deep Q, of course. In cylindrical coordinate system, remember that this is going to be what? This is going to be 1 upon what? 1 upon h1, h2, h3. We've done all this. h1, h2, h3 times what? That is die u1 of what? Of the scalar of the other two. Scalar factors of the other two. If we are along u1, we use this to multiply this. That is h2, h3 times the components of q. The components of q, that is component of q along this, that is q what? that is Q, it must agree with this, Q1. Then, having known this first one, it's very easy to know the rest. So when you are now finding that of U2, for U2, if you are using U2, the components of the other, and you multiply the factors of the other two, that is H1, H3 of what? H1, H3, this one must agree what is here. Q what? Q2. Because the last one, of course, when you are here, follow the same trend. That is, this one is H1, H3. So this is U3 of what? That is H1, H2 of what? Of Q3. Because this is, so if you substitute into it, time does not allow us to do that, you get the value. For example, if we expand this in the cylindrical coordinate system, what would it be? In the cylindrical coordinate system, the expansion of this now give you what? To expand this, because H1 is what? Is 1. Abi? Or let me put it this is the same thing now. If you are in cylindrical coordinate system, this is the general one tensor. So that means this is 1 upon H along R. That is HR, H theta, and H what? HZ into what? That is di, because U1 is now R, right? Di R of the other two, that is H theta, HZ of velocity along R, that is QR. Of course, once you know the first term very well, others follow the same trend, you don't need to start cramming. So that is di theta of what? That is HR, HZ of Q what? Q theta. And finally this one, that is di Z, that is other, that is HR, H theta of what? QZ. So that's the expression. So that is the, so it is in this expression now, you can now substitute for your HR, H theta is Z. So HR, if you multiply the three of them, this and this and this, of course, the answer is still going to be what? R. You still get R, because 1 times R times 1, that is R. Then you now have di R of what? Of, because this one is R, this one is 1, that is R times what? QR plus di theta of, again, HR is 1, AZ is 1, so all of them. 1 times 1, that is Q theta. Finally, di Z of HR is 1, H theta is R. So that is R times what? Q of Z. That is going to be the divergence. Of course, you can see that what happens here, RQR is the same thing as RQZ, because R is the component of this one multiplying them. So that's that. Then, in that wise, it is very easy to find the Q, just as, and it is also easy to find what you come across again is del square. You will come across this operator. You come across this operator. How do you expand this in cylindrical coordinate system? In general, this is going to be 1 upon what? You have it in your note. That is H1, H2, H3. In general case of what? Then now di U1. Then take note, it's different from this expansion. Of course, it's part of what I asked you people to do that time. So the scalar, the multiplication means that is H2, H3. Though this time around, you divide this one by H1. Then di U1. That is the expansion of that. Because you are changing to that coordinate system. Of course, knowing this first one very well, others follow the same trend. So the other one will be di U2. Now the other two, that is H1, A3 upon what? H2. Di U2. So we can write the last one now without loss of generality. The last one now is what? That is plus di-U3 of what? The other two, that is H2, H1, that is H1, H2 upon H3, di-U3. Okay? So that is the expression. You can see clearly that if this is U1, all these they agree. You see, 1, 1, 1, 2, 2, 2. So you can see 3, 3, 3. So if you know this is an hungry operator, whatever you put it inside, slot it in, it will work. When you slot something in here, because it will work, it will operate on that. Now, in cylindrical coordinate system, what would it be? Seems I'm wasting too much time on this thing. H1, di-U3. Okay. So, if you translate it to cylindrical coordinate system, therefore, in cylindrical coordinate system, this will be what? If you multiply the 3, 1 times R times 1, that is 1 upon R of, but this is R, that is di-R of, if you multiply, this one is R, this one is 1, that is R over 1. So I don't need to start wasting time on that. di-R. This will be the first one. Then followed by this, the second one here. So this one is, under this case, U is theta, so that is di-theta of H1 is 1, H3 is 1, and H2 is what? Is theta. H2 is what? Is R, sorry, is R. H3 is R. So that is 1 upon R of what? Of di-theta. That because H1 is 1, A3 is also 1, but H2 is R. So that is that. Then finally, for this last one, that is di-Z. It will look like this. Because H1 is 1, H2 is what? H2 is R. No, H1 is 1, H2 is R, A3 is 1. So it is also R of what? Di-Z. So that's that. Or sometimes if you like, you can expand it out. You can expand it out and several others. Now, let us move back to where we are going now. Because I cannot do everything for you. You sit down at your leisure time to the right. Then, another important thing of interest is how do you find d dt? Don't forget, d dt is what? D dt is di-t plus what? Plus q dot, that's Navier operator. This is material derivative. This one is local derivative, and this one is the convective part. So how do we do it? So if you recall very well, you see that this can be expanded. In a rectangular coordinate system, you can do it in rectangular, in rectangular coordinates. In rectangular coordinates, this can be written as what? Because in rectangular coordinate system, Q is what? Q is UVW, isn't it? So in rectangular coordinate system, because in this case, Q is UVW. So if we expand this, that means d dt, we have mentioned it before, it is the same thing as di-t plus, you multiply this with this, that is going to be u times di-x. You multiply with the other component, that is b times di-y. And finally, W times di C. That's that. So similar things take place in the other coordinate system. In the other coordinate system, like this is of interest to us. In cylindrical coordinate system, how do we find this? In cylindrical coordinate system, how do we write this? Because I will jump to the result, but at your convenient time, I want you to sit down and establish it. That is why I'm showing you what might cause problem along the line in the derivation. So, in that way, in cylindrical coordinate system, time is not, but you need this part. In cylindrical coordinate system, what is Q? What is that? In cylindrical coordinate system, in cylindrical, coordinates, which is coordinate what? R, theta, Z. That is cylindrical. Then how do you find this? You know that Q is what? Velocity, free velocity, velocity Q as component what? Q along R, Q along theta, Q along Z. Is it? And don't forget the scalar factor. Scalar factors stand for what? H along R, H along theta, and H along Z. Don't forget, in cylindrical this is 1, in cylindrical this is half, in cylindrical this is 1.